is my domain, domain. You're in my kingdom now. This is my domain, domain. No one can tear it down. This is my domain, domain. You're stepping on my ground. It's live or die my way. Inside the walls of my domain.
So just like the song suggests, in this video we're going to talk about domain and range. Domain and range are so cool that my math team made up a cheer. Yes, it goes like this. When I say domain, you say X values. Domain, X values, domain, X values. When I say range, you say Y values. Range, Y values, range, Y values. Go math team. Okay, I joke, but in reality, domain is just your X values or your valid inputs. And your range is just your Y values or your valid outputs. Now, if we have a relation, which relation is just a fancy word for a set of points, it's pretty easy to see what the domain and range will be. Now, I've used set notation here. I've called this set S. This is just the name of the set. We use a colon and this bracket. I actually call this the squiggle bracket so we don't get them confused, to denote what our relation is. And inside the relation, each one of these is a separate point separated by a comma. All right, and now when we look at an individual point, we know that on the left is our X value and on the right is our Y value. And so when we're asked to find the domain or X values from a relation, we're just going to look through and list all of the different X values. Now there is only one or two rules to keep in mind as we do this, and that is that when we list them smallest to largest, and if one were to repeat, we only list it once. So I'm going to call my domain D because I'm really creative like that. I'm going to use that squiggle bracket, and now I'm just going to list all my X values from smallest to largest, not repeating. So I see that my smallest X value is -5, comma, -3, comma, 2, 4, and 7. And now again, I've used set notation here, listed all of my X values and separated them with a comma. Okay, and for the range, we're going to do something similar. I'm just going to call that R. All right, and now we're going to look through and do all of our Y values, because when I say range, you say Y values. Again, we're going to list them smallest to largest, and if they were to repeat, we only list them once. So my smallest value is -7. Looking through here, I have a -2. I have a 5, and notice that 5 occurs here and here, but I'm just going to list it once. And then I have a 12. Okay, so this would be the domain of this relation, and this would be the range of this relation. And notice that if we know the domain and range, we can't necessarily work backwards. Notice that this -5 doesn't go with this -7. 2 actually goes with -7. So really there's no way to map back to our relation from our domain and range. Okay, but that is what it would be. Now, when we're looking at a graph, okay, you can see here that -2, all right, might be in there, and 0 is in there, but notice that we've included every value in between. So now this is different than a relation in that we got to include all of the values. So when I think about the domain, again, we think about the X values, and we know that our X values run from left to right, okay? And when I start to think about this, when I think about the domain, I think about and the range for that matter, I think about building a house. And what I'm going to look for in the domain is the walls to my house. In other words, if I wanted to wall in this function, where would I construct that left wall? Well, that would go right here. Where would I construct that right wall? Well, that would go right here. And if I put those walls on this function, it would never go outside there. How do I know that? Well, these dots tell me that the solid circle or dot tells me that the function ends here. So it's going to, or begins here, which, and then I have an open circle here. And what does that mean? Well, if it's solid, it means it can equal that value. For example, -410 is actually on this graph. if it's open, it says it gets really, really, really close to that value, but never quite equals it. For example, 2, -2 is not on this graph, but like 1.99999 minus 1.99999 is, okay? So we get really, really close. Now, why is that important? Well, it's going to be important when we get ready to state our domain, okay? All right, so when we talk about domain, we talk about x values, and then we want to talk about the left and the right wall. So on the left side, it's bound by the smallest x value this ever takes on, which is going to be -4. And on the right, it's bound by the largest x value this ever takes on, which is 2. And now the open circle corresponds to a less than sign, no equal. And if we have a solid dot, we put the equal. Because again, this tells me that it can equal -4 here because that's a solid dot. It can get really, really, really close to 2, but it can never quite equal 2, so because that's an open circle. All right, so our walls are our domain, and when we think about our range, it's going to be our ceiling and our floor. So where would I construct my ceiling? Well, if I was boxing in this function, I would put my ceiling there, and I would put my floor here. Okay, so when I say domain, you say x values. When I say range, you say y values. Okay, and now the smallest y value this ever takes on is -2, but notice that we didn't quite get there because this is an open circle, so I'm going to use just a less than sign. And the largest y value this ever takes on is 10. And now we're going to use the equal sign with that because we have a solid dot. Okay. All right, let's try one more example. Again, what we're looking for on this graph is the domain, x values, and the range, y values. Okay, so domain is our walls of our house. So I could construct that here and here. Okay, and so when we state this, remember domain is x, so I'm going to use the x variable. The smallest value it ever takes on is -5. It's a solid dot, so I'm going to use the equal sign there. And on the right, it is bound by here, +1, okay? And now this gets a little tricky for the range, but what we're trying to do is box in this function, and so we would construct it here, okay? Notice we don't go to the endpoint always. It's the largest value it takes on, but because this goes up and then comes back down, we're going to concentrate on right there. And then the smallest value would be down here. All right, so for our range, we think y value, so we're going to use a y. The smallest y value this ever takes on is down here at -20. Solid dot, going to use the equal sign. And the largest y value this ever takes on is 1. Okay, and again, equal sign. All right. Now that brings up the question of how would this change if we don't have dots on the end, but we have arrows. Okay. So again, let's pretend that we have this function, but now we're not going to stop it. We're going to put arrows. And we know that arrows means Energizer Bunny, right? Keeps going and going and going and going and going. Okay? All right, so how is that going to change my domain and range? All right. Well, now when we think about the x values, if I try to construct a wall, what's going to happen? Well, I could build one here and build one here, but my function's still on the other side. So my walls are going to have to keep going and going and going. Energizer Bunny. We know way out here is infinity, and way out here is -infinity. So there's several ways to state this. We might say all real numbers, okay? All right, you might see it written in interval notation, which is -infinity to infinity. That would be two different ways to write the domain in this case. But in other words, this keeps going and going and going, so we're going to include all x values. It's defined for every x value, in other words. Let's look at the range in this case. Well, if we look at the smallest y value this ever takes on, well, this keeps going and going and going, and way down here we have -infinity. Okay, so this is going to keep going and going and going down to negative infinity. All right, but we see that this also keeps going down, down, down to negative infinity. But my graph never gets above this value here. So it is actually going to be bound by positive 5. In other words, the range of this function is any value less than positive 5. So you might write it this way to see that it's bound, but remember that this would also mean the same thing as this. Y is always less than or equal to 5. Okay, so we can construct a ceiling here, right? In other words, we can put a cap on it. It never goes above 5, but we can't put a floor on it, meaning that it's going to keep going and going and going. If I tried to build the floor here, it would go past that, and we keep going and going. All right, so that's how we find the domain and the range of a graph. And what's so different about this than the relation is this means it can be any value between negative 4 and 2. In other words, it could be 1.5, it could be negative 2.73, okay? In a relation, it is these finite numbers. Negative 5's in there, negative 4 is not. Negative 4.5 is not. Negative 1.5 is not. Okay, the only thing in this domain is negative 5, negative 3, 2, 4, 7. So in this case, we have a finite set of numbers, but when we look at a graph, we're going to have a continual set of numbers, everything in between those. And now I talked about it in the beginning. Valid inputs, valid outputs, and I just wanted to go back to that and show you kind of a real world example. This is a graph of men's foot length in inches and then their corresponding shoe size. And if you know anything about men's shoes, you know that pretty much you can't buy men's shoes until you're in a 6, maybe even larger. And this is probably not as realistic as it needs to be, but we'll just say that the largest men's shoe size you can ever find in a store is a 15. It's probably more like a 13, but we'll pretend. All right. So what this means is if a guy were to stand on a ruler and measure his foot, and he got his foot to be 10 inches long, he would wear approximately a 6. Now, this isn't exact because people like their shoes to fit different. But in theory, if they stood on a ruler and was 10 inches, then he'd wear a size 6. Okay, so this is the length of a guy's foot in inches. Notice that 2 is not a valid input, right? Even when you're born, your foot is longer than 2 inches. Negative numbers are not valid inputs. Can you ever have a negative 2-inch foot size? Well, no. All right, so for this particular model, the only valid inputs are between 10 and 13, right? And in reality, that would be my domain, okay? In other words, I would say to use this graph or to use this relationship, you have to have a foot length between 10 and 13 inches. Those are my valid inputs. And my valid outputs, all right, that we just talked about is between 6 and 15, and that would be my range. In other words, if you're Shaquille O'Neal and you wear like a 25, this chart is not valid because that's not a valid output for this chart, okay? If you're wearing kid sizes, you can't use this chart. So this just starts to tell you what we mean by valid inputs for a graph, which in this case would be 10 to 13, and valid outputs, which in this case would be 6 to 15. Okay, so again, this just puts it in perspective why domain and range are important. I hope you've enjoyed this video. I look forward to seeing you next time.
This is my domain.